Hello. So I hope you guys had a good nice last week of summer. For me, school starting on Monday, and I still have to finish up my history assignment. Hello. So it's 8 o'clock for me, and I'll wait maybe 1 or 2 more minutes. Hello. Hello. So share my screen now. So as you can see, this week is the first week of fluids, and next week we'll have fluids again. And then the last week will be simple harmonic motion. So before we start, I would like to say that this class is not all of physics. So the things we're discussing in this class, all up to week 18, those are what we call mechanics. It's like a subsection of physics. And there's actually a lot more to physics than just mechanics, but mechanics is what people generally think of when they hear the word physics. So physics can also have applications in thermodynamics, which is about heat and all that kind of stuff. It has applications in electricity, in magnetism, in light, and all other things. So after this course ends, I might have an electricity course because that's also very essential to physics. So I might have another physics course after this one, if there are enough people that will participate. Okay, so but if there's not that many people, then I won't be giving the class. All right, I'll start the class now. So week 16 is fluids, and the fluids we will talk about today are fluids that are static, which means that these fluids can't move, okay? Whenever you have water flowing out of the tap, that fluid is moving. So we're not going to be talking about that for today. That will be next week. Next week will be moving fluids. This week is static fluids. These are all the things that we can apply to static fluids. Okay, I'll get started. The topics are, first of all, what are fluids? Then we have density, pressure, Pascal's principle, and Archimedes' principle. Okay, so some of these things aren't specific to fluids, but some of them are specific to fluids. Okay, so first of all, what are fluids? When people think of fluids, they think of a liquid like water. That's correct. A liquid is a type of fluid, okay? But in the physics definition of a fluid, a gas is also a type of fluid, okay? So a fluid is either going to be a liquid or a gas. So for all of this course, before, we've been talking about solid objects, even if we had a rolling object, it was still a solid ball, right? We had a solid hoop, we have solid boxes, pulleys, all those things. Those are solids. So we're going to be talking about fluids now. So what makes fluids different from solids is that a fluid cannot maintain its own shape. So it has its unique properties. Okay? So a fluid can be either a liquid or it could be a gas. Okay? So that's what a fluid is. So let's go on to something called density. And density is actually not specific to fluids. Density is something that can be applied to everything. But density is really critical when we talk about fluids and all the physics between fluids. Okay, so what is density? Density is defined as an object's mass per volume. Okay, so when you say, some people might say that steel is heavier than feathers, but it depends on how much steel, how much feathers you have. So the better way to say that is by saying steel is more dense than feathers. It's heavier per unit of volume. Like if you're to fill up a room, if you were to fill a box with steel, that would be a lot heavier than a box of feathers. Okay, and the density of an object, the symbol we use to write density is this symbol. It looks kind of like a P, but the top of it is curved. It kind of curves in like this. It's like an upside down 6. Okay, and this is the Greek letter rho. I pronounced rho. So when I say rho, that's the thing I'm referring to, and rho is the density. Okay, so if I ask the rho of steel, that will be the density of steel. Okay, so that is the symbol we use for density. And the units we use for density is, well, for mass, we have kilograms. And for volume, we use the meter for length. So for volume, we'll use the meter cubed. So the unit for density we're going to be using in our equations is going to be the kilogram per meter cubed. But you may ask, there's another unit of volume that I know that's in the metric units, right? The other unit of volume is the liter, right? So why aren't we using the liter? Well, for volume, for length, in physics, we use the meter. For area, we use the meter squared. So we have to use the meter cubed for volume as well. That's why we can't use liters. But you should learn how to convert between liters and meters cubed, okay? These are different units of volume that you'll need to convert between, because sometimes the problem will give you volume in terms of liters instead of meters cubed. And you'll have to transfer the liters into meters cubed, okay? So the conversion factor is actually 1 milliliter is equal to 1 centimeter cubed. Okay, so that's the conversion factor. 1 centimeter cubed, 1 cubic centimeter is equal to 1 milliliter. Okay, that means 1 liter is 1,000 centimeters cubed. So to convert that to meters cubed, well, 1 centimeter, 100 centimeters is 1 meter. So 100 centimeters cubed is 1 meter cubed. So that means 1 million centimeters cubed equals 1 meter cubed. Okay? So 1,000 centimeters cubed is the same thing as 1/1000th meter cubed, which means that 1,000 liters equals 1 meter cubed. So this is the conversion factor between liters and meters cubed. So whenever you use your equations, you'll have to convert from liters into meters cubed. All right, so now let's look at the table I have here. We have a table of some densities of objects. Okay, so as you can see, we have, let's say we have aluminum that has a relatively high density and air, right? We can see how the density, rho, is much larger for aluminum than it is for air. Okay, so you may see that at the top of the table, there is something that says standard temperature, 0 degrees, and atmospheric pressure. What does that mean? Well, the density of an object is actually not set. It's not set in stone. You may know that because when we increase the temperature of an object, if we increase the temperature of water, that decreases the density of the water because then the water molecules are farther apart. Okay, so if we change the temperature of a solution, the density can change. And also if we change the pressure, that also changes. So temperature and pressure both affect the density of a fluid. Okay, but how that affects the fluid, that's not for this course. That will be in thermodynamics. So for this course, for now, we're just going to use the values in this table. Okay, so whenever we have a problem with the density of an object, you'll just use the value from this table. We'll be assuming that it's at 0 degrees and at atmospheric pressure. Okay, so because of that, we're going to be using some of these values later on in the class. So you guys should take a screenshot of this table so that you can reference these densities later on. Okay, so you don't need to memorize these densities. You need to take a screenshot of this right now so you can use the values later on when we do the problems. Okay, so I'll give you a second to take a screenshot. Alrighty, so for the majority of the values in this table, you won't need to memorize them, but one of them you do is water. The density of the water, you're going to use the density of water a lot. Okay, so the density of, when I say the density of the water, I mean pure water. So for this table, you will be looking at fresh water, 1,000 kilograms per meter cubed. That's the density of pure water. Okay, so you're going to be using the density of pure water. So you may ask, why is there a difference between the density of fresh water and seawater? Well, in seawater, there are a lot of other things like salt and minerals and all those things. So when we want to talk about pure water, we're going to have to use the density for fresh water. So out of all of the values in this table, the one thing I need you to memorize is the density of fresh water. And that shouldn't be too hard to memorize. All right. So let's do some problems now. 3 problems about density. When you get your answer, you can chat that to me and I'll let you know if you're right or not. So someone came in late, so I'm going to move the slide back for them to take a screenshot of the table. So if you came in late, please take a screenshot of this so you can use these values later on in the class. All right, switch back. more minute. Okay, I'm going to explain now. So the first one, we're just going to use the formula rho, which is pressure, which is density. Rho equals mass over volume. So to find mass, we're just going to do rho times B, which is going to be, well, if we look at our table here, the density of iron is 7.86 times 10 to the third. Multiply that by the volume of a sphere. So this is going to be 4/3 pi 0.18 cubed. So our answer should be 192 kilograms. Okay. The next one is the same thing. Rho equals m over v. So to find volume, volume is going to equal to mass over rho. 1 over 1,000. 1,000 is the density of water. Our answer is going to be 0.001 meters cubed. Okay. For the last one, we have to change the units for density from kilograms per meter cubed to grams per milliliter. Okay. So how do we do this? Well, let's first write out these units. To get from kilograms to grams, what do we need to do? We need to multiply by 1 over 1,000. Okay, because there are 1,000 grams in a kilogram. Now from meters cubed to milliliters, what do we multiply that? Well, from meters cubed to centimeters cubed, we multiply by 1 over 1 million, which is 100 cubed, right? There are 100 centimeters in a meter, so there are 1,000,000 centimeters cubed in a meter cubed. Then we multiply by 1, okay? Because there's 1 centimeter cubed in 1 milliliter. So note how these are in the denominator, so we need to take the reciprocal as our conversion factor. So it's actually going to be 1,000. So if we multiply by 1,000 million times 1 over 1,000, then we get 1,000. Okay, so there are 1,000 kilogram per meter cubed inside 1 gram per milliliter. Okay, so to get from kilograms per meter cubed, we just divide it by 1,000 to get the grams per milliliter. So this will turn into 2.7 grams per milliliter. All right, any questions? All right. Now we have pressure. Pressure is, like density, pressure is very critical to our observation of fluids. And pressure, the formula for pressure is defined as a force over an area. And the label we have for pressure is just a capital P. Okay? So pressure is force over area. If I apply a force to a certain area, then that will equal to the pressure. So one example is if an apple falls from the sky and it hits the ground like this, and it kind of squashes a little bit when it hits the ground. So let's say the contact area with the ground is A, and the impulse and the force exerted from the ground, the normal force, that is F. So the pressure exerted on the apple is equal to F over A. So why do we use pressure and not force? Because pressure depends on the unit area applied. So one example is if you were to take a pencil, okay, and you were to put that pencil with some sort of force onto your arm, it will hurt, right? But if you put, let's say, something bigger with bigger area, like an eraser, on the same force, it doesn't really do anything because the surface area in contact with your arm is greater, okay? So when A is greater, the pressure is less. Okay? So pressure depends on the area. Okay? So pressure is actually really critical to fluids because there is a theorem. Okay? There's a theorem that states, let me write it out here. This theorem states that a fluid exerts pressure in all directions. So what does this mean? Let me say I have a glass of water. Okay, so the glass of water is a fluid, and this water is going to exert a pressure in all directions. It's going to exert a pressure outwards on the sides of the glass. Okay, this is because if the glass were to suddenly disappear, the water would all spill out this way because of the pressure. Okay, so a fluid exerts a pressure in all directions. So it can exert a pressure outwards. It can also exert pressures inward. So if I were to drop a small cube into this water, the water will exert a pressure in all directions on the cube. It will compress the cube inwards. Okay, so a fluid can exert a pressure outwards and a pressure inwards on an object inside the fluid. Okay, so there's pressure exerting on this cube in all directions from the fluid. Okay, so on a molecular scale, why this pressure exists is because when we have an H2O molecule right here, it's moving in random directions, right? So if the molecule were to hit the wall and bounce off, it would exert a tiny pressure on the side of the wall, which means that overall, when we consider all of the molecules, there's a kind of a big pressure on the sides of the wall. And similarly, why there's a pressure on the cube inside? Well, another molecule could be going at the cube and it would bounce off, which would exert a pressure on the cube. Okay? So one thing to note about a pressure that adds on to this theorem is that pressure in a fluid increases with depth. So the lower you are in a fluid, the greater the pressure is. So one example is if you were at the surface of the ocean, the pressure acting on you would be less, right? It wouldn't be that much. You wouldn't get, you would be fine. But if you were to move down to the bottom of the ocean, like in the Mariana Trench, for example, you may know that when you go down there, the pressure is so overwhelming that it will crush you immediately. Okay, so a fluid increases with pressure with depth. So why is this true? Well, here's the proof. Okay, so let's say I have a huge container of water or any kind of fluid. Okay, so a huge container of water. And I have a thin metal plate. Okay, it's a thin metal sheet, a square piece of metal with cross-section area A. Okay, with surface area A. Okay, so the area of the metal plate is A. So basically how we visualize the pressure of a fluid is by the mass of the water above it. So imagine that we were to draw a small box with all the water contained inside of it above the metal plate. Okay, because there's a large chunk of water above this metal plate, right? So we basically believe that this metal plate needs to hold up all the water above it, okay? Because this water is pretty heavy. So when this metal plate needs to hold up all the water above it, the water exerts a pressure downwards on it. So how do we calculate this pressure? Well, the pressure is equal to force over area, which equals the mass of the water times G, which is the weight of the water, divided by the area of the plate. Okay, so this is the pressure caused by all the water pushing down on this metal plate. Okay, so we can rewrite this formula a little better. Because the mass of the water, we know that rho equals mass over volume. So mass equals rho times volume. So let's replace mass here with rho Vg over A. So this is the volume of the water multiplied by the density of the water to get to mass. We can rewrite this even further because the volume of the water, if the box is at a depth h under the ground, if the metal plate is at a depth h below the water, because we got to consider depth in here, right? Because the theorem relies on depth. So we know that A times h equals volume. That's basically the volume formula. So we can replace volume in this equation with A times h. So pressure is rho A h g over A. Oh, look, the A's cancel. Pressure equals rho g h. And this is the formula for the pressure exerted on an object at a depth h below the surface of the ocean or any other fluid. Okay, so the density of the fluid multiplied gravity multiplied by the depth. Okay, so this pressure, I'll say it again, it's not just the downwards pressure on the plate. Okay, because if I were to draw the plate again, the pressure going downwards, yes, right, because that is the weight of the water. But we know that pressure exerts on the fluid exerts the pressure in all directions. So this is the same pressure pushing the plate up from the bottom, pushing the plate to the right, to the left. On all directions, the pressure is equal to this value. Okay, so the pressure is equal to this value in all the directions acting on the plate. Okay, are there any questions about this? Cool, so that is the formula for the pressure acting on any object, or even the wall here, okay? The wall of the container, the pressure exerting outward on the wall is equal to rho g h, okay? So there is still a lot more to talk about the pressure. So one other thing about the pressure in a fluid is that for a fluid at rest, okay, specifically for a fluid at rest, this pressure is exerted perpendicularly to surfaces. So the pressure, if we have water at rest in the container, the pressure is always going to be perpendicular to the container faces. And if we have the cube again, the pressure is always going to be perpendicular to the faces of the cube. For any fluid at rest, that's the nature of the pressure. Okay? So you may be wondering, what are the units for pressure? What units do I use? Well, for units, pressure is force over area, which makes it equal to newtons over meter squared. And there's actually a special unit for pressure, and that equals to the newton over meter squared, and that is called the Pascal, labeled with a PA. So we're going to discuss a theorem or a principle by Pascal later on in the class, and he's basically the unit of pressure is named after Pascal. So when I say 1 Pascal, that means 1 Newton per meter cubed. Okay, so those are the units for pressure. So there's one last thing I need to talk about for pressure, and that's with the air pressure exerting on people on the ground. Because when you go outside, for example, you are holding up a whole column of air above you in the atmosphere. There's a ton of air above you. So this air is pushing down on you with some kind of pressure. And in all directions, you're feeling this pressure. Okay, so experimentally, scientists have figured out that the pressure at the bottom, at the Earth's surface, due to all the air above you, is equal to 1.013 times 10 to the 5th pascals. So this is something you should write in your notebook or something like that. So this is the pressure exerted on all the things due to the air above you on the Earth's surface. Okay, so this is the pressure that scientists have experimentally tested out. And this number is actually called, there's a special way to describe this. It's called 1 atm. So 1 atm is 1.013 times 10 to the 5th pascals. So this 1 atm basically means 1 atmospheric pressure. Okay, so this is the pressure acting on any object at the surface of the Earth. So one question that you may have is that, hey, if I calculate, let's say we have the ocean here, and we want to calculate the pressure at this point, P. What's the pressure? Well, we can calculate the pressure from just the water with rho gh, right? That's the pressure from just the water. But what about the pressure exerted downward from the air, right? Isn't the air pushing down as well? Isn't this point P handling all the water plus the air on top of it? So will we have to add the atmospheric pressure to our answer? Well, when you give your answer, there are actually two types of pressure you can give. One of the types is called gauge pressure. And when the problem asks for gauge pressure, it basically means that you ignore the atmospheric pressure. You don't include the atmospheric pressure, which means your answer is just going to be rho GH. All you include is the water, okay? If we do include the atmospheric pressure, it's called absolute pressure. Absolute pressure. This is rho GH added to the pressure above you, which is going to be the pressure of atmospheric. Okay, so these are the two types of pressure you can give as your answer in the problem. So the problem will specify what answer they want. Okay, they're either going to ask for the gauge pressure or the absolute pressure, so you're going to have to look out for that. So the reason we have these two different types of pressure is that if we ask for absolute pressure all the time, it gets a bit redundant because all we need to do between the gauge and the absolute pressure is add this constant to our gauge pressure to get to our absolute pressure. So that's why, to save you some time, most problems will only ask you for gauge pressure. Okay? So is everyone clear about pressure?
How many, wait, actually, never mind.
Okay. We have problems now. Here are two problems. When you get your answer, you can chat that to me and I'll let you know if you're right or not. One more minute. All right, I'm gonna explain this now. So for the first one, you want to find the pressure or the force acting on you. We're gonna use the formula that pressure is force per unit area. Force is equal to pressure times the area applied. It's just gonna be 1.013 times 10 to the fifth times 0.2. I think this is gonna be 2026. Okay, newtons. So this is the force pushing down on us when we go outside. So this is actually a whole lot of force, right? This is a lot. So why do we feel like there's a whole weight pushing down on us from above? So the thing is, we're made of cells, right? So the liquid in the cells, there's fluid inside the cells, and the pressure inside the cells, because any fluid has pressure, right? So the pressure in the cells is regulated so that it's roughly equal to the atmospheric pressure. So we basically don't feel that force at all, okay? So now for the second problem, the Mariana Trench is 11 kilometers deep. What is the gauge pressure on the flounder at the bottom of the trench? So basically use the pressure for fluid at a depth h below the ground is rho gh. Since it's water, we're going to use 1000 multiplied by 9.8 multiplied by h, which is 11,000. Okay, so calculating this real quick, I think it's around 107 with some kind of zeros after it. Do you have a question?
Shouldn't rho be one, like, isn't the for seawater, isn't it one?
Oh yes. You are correct. The density of seawater is bigger than freshwater, and you are correct by that. But in most problems, the difference is going to be so little that it doesn't really matter. But that's a good point, okay? So my answer is a little bit off from what it's actually going to be, but it's roughly the same thing, okay? So now if we want absolute pressure, all we need to do is add the pressure from the air above the water. And we know that's going to be equal to 1.013 times 10 to the fifth. So if we add this to this value, we're going to get the absolute pressure. But since 1.013 times 10 to the fifth is so little compared to the gauge pressure, we're not even going to include it because it's insignificant. It wouldn't really matter if we included it anyways. Okay, so we're going to basically consider the gauge pressure equal to the absolute pressure in this scenario. Okay, so if the flounder has a cross-section area of 0.1 meters squared, what is the force acting on it? Well, pressure equals to force per area. So force is equal to pressure times area. So if you were to multiply this value by 0.1, you get your answer. All right, any questions? Cool. Now I've got a slightly tricky problem here. Give it a shot. This is actually pretty tricky, so I wouldn't really expect you guys to get this on the first try, but give it a shot. I'll give you guys 2 minutes, and once you get your answer, you can chat that to me. I'm going to explain this one now. So at first look, you may think, hey, pressure is generated by the weight of the water above the bottom of the flask. So if we draw an imaginary line here, we're going to need to calculate the volume of water or the mass of the volume above the bottom of the glass, and that will be our pressure, right? But no, that is not right, because from what we know about pressure, a fluid exerts a pressure in all directions, which means this water inside this flask is going to exert a pressure outwards perpendicularly on the walls of the flask. Okay? According to Newton's third law, the walls of the flask will exert an equal and opposite pressure on the water. So on the water, there's a pressure going inwards by the walls of the glass. And as you can see, this pressure can be divided into components. And there's a downward component of pressure acting on the water. And this pressure will eventually travel down to the bottom of the glass, and there's added pressure at the bottom. So we need to include the weight of the water and the pressure exerted by the walls of the glass. And the cool thing is that when we add these two things together, our answer is still going to be rho g h. Okay? So the cool thing is about this formula is that h is the height, or h is the distance between the bottom and the highest molecule of water. Okay, so this is the distance between the bottom of the flask and the highest molecule of water in the flask. Okay, so if you were to take the highest one here and compare it to here, the height is 2 meters. So our formula is just going to be rho gh 1000 times 9.8 times 2. Okay, so it doesn't matter how the glass is shaped. All that matters is the net distance between the top, the uppermost molecule of water, and the bottom of the glass. So even if the glass was shaped like this, and want to find the pressure at the bottom here, the pressure is still going to be rho gh. Okay, so that's the really cool thing about this formula. It doesn't matter how the glass is shaped in any way. It only depends the net height between the uppermost glass of water, the uppermost molecule of water, and the bottom of the glass. Okay? And one thing to note about this formula is that the whole glass needs to be open. Okay? Because if I were to close off the glass right here, it's almost like we have two separate glasses. So if I closed off the glass here, then we would have to compare H from this point. Okay, so you got to be pretty careful. If the problem has like a valve stuck in there and that blocks the water, your height is actually going to change. It's not going to be the net height between the uppermost. It's going to be the height up to the glass or the valve. Okay, are there any questions? All right, so now you know this. Here are two problems from the 2017 F equals MA. Now that you know that formula, I don't think these should take that long, even though they're pretty challenging. So when you get your answer, please chat the letter that corresponds to the right answer to me. So for the first problem, you got to read the problem a little more carefully because they like to trick you in these competitions. I'll give you 1 more minute. Okay, I'm going to go through these problems now. For the first one, you got to read the problem really carefully, okay? Because if you're not going to read the problem carefully, you're going to get the wrong answer. So the critical sentence in here is that it says an equal volume of water is poured into each flask. So the same volume of water is poured into each flask, which means that in this flask, let's say the height of water is here, okay? Let me draw it a little better. But in the second flask, it's open wider, which means logically the water is going to be at a lower level in this glass. The top glass is narrow at the top, which means the water will be highest in that glass. Okay, so you got to read the problem really carefully because it says this equal volume of water is poured into each glass, which makes the height different. Okay, so now we can compare the heights. The greater the height, the greater the pressure, which means highest, medium, lowest. C, A, B. D is the correct answer. Okay, the next one, it's basically the same thing. You're going to have to compare the bottom to the highest point of water. The highest point of water is not here. It's at lowercase h, rho g, lowercase h. The answer is A. Okay. Are there any questions? Alrighty. Now we're going to move on to Pascal's principle. But before we move on, I'm going to leave a little disclaimer that I think I'm going to have to go over time again. Sorry about that. It's going to be like around 15 minutes over time. So if you do need to leave at 9 o'clock, feel free to do so. So Pascal's principle is a principle that's really critical to fluids. And the principle goes like this. Okay, let me write it like this. If any external pressure is applied to a fluid, every point, okay, the pressure at every point in the fluid increases by about. This is Pascal's principle. It says that if any external pressure is applied to a fluid, the pressure at every single point in that fluid will increase by that amount. So one example is if we inflate a balloon, okay? Because if you're going to add a pressure inwards from the opening of the balloon, you know how the walls of the balloon, they all expand out in equally, right? They expand out in equal magnitudes, right? It's not like this side of the balloon will expand farther than this side. The whole wall of the balloon is going to expand out at the exact same rate, at the exact same magnitude. So this is basically Pascal's principle. It says that if any external pressure is applied to a fluid, every single point in that fluid increases equally by that external pressure. Okay, so another example is for a tube of toothpaste. Okay, if we have a tube of toothpaste, let me draw like this. Okay, if we apply a pressure, like if you're to squeeze the tube of toothpaste, applying a pressure on the tube, we know that the walls of the toothpaste tube are going to bulge out, and some toothpaste is going to come out from the end. Okay, that's because the toothpaste, when we apply an external pressure into the toothpaste, the whole toothpaste increases with that pressure, which means that the pressure causes a force, which will force the toothpaste out of the opening. So this is Pascal's principle. If any external pressure is applied to a fluid, every point in the fluid increases by that pressure. So this is basically the proof for our formula for absolute pressure, right? P absolute, we know that's rho GH plus P atmosphere, right? Because if we consider the atmospheric pressure as our external pressure, we know that if we have that external pressure applied to the fluid, then every single point inside that fluid is going to increase by that amount. So we add the atmospheric pressure to get to absolute pressure, okay? So one common application of Pascal's principle is with the hydraulic lift. Okay, so let me draw out one example here. At the mechanic, they have a hydraulic lift, which will lift up really heavy objects. Let's say we have a car on this end, very heavy car. On this end, we have, let's say some person steps on. We know that by Pascal's principle, external pressure, any external pressure applied to a fluid is going to increase the pressure at every point in that fluid, which means that when the person steps on the piston here, let's say this is a piston, when the person steps on the piston, there's a pressure going in, okay? And the pressure inside that fluid increases equally. The pressure on this wall is going to increase by that amount, right? But the wall of the container, it's structurally sound, so it will not like explode or anything, right? So it will stay that way. But if the car is attached to a piston, the piston can move. So the external pressure is going to increase the pressure acting on the piston, which means it exerts a pressure upwards, okay? So this is one common application of Pascal's principle. If we apply a pressure inwards right here, an equal pressure goes out. So P in equals P out. So let's say the area of the piston on the left is A1. The area on the piston on the right is A2. We have F1, F2. So P1 equals P2, which means that P1 F1 over A1 equals F2 over A2. If we rearrange a little bit, we get F1 over F2 equals A1 over A2. So this means that if A2 is a lot bigger than A1, this means that F2 will be a lot bigger than F1. So this is why I drew the diagram in this way. Since A1 is a lot smaller here, the magnitude of the force going in is a lot smaller than the magnitude of the force going outwards, because there's a large area over here. So this is actually called mechanical advantage, because we apply a smaller force inwards that gives us a greater force going out. So this is why a small person can lift up a car using hydraulics. Okay? So this is one common application of Pascal's principle. Are there any questions? Cool. So we have one problem involving Pascal's principle, basically to give you a clearer idea of how the hydraulic lift works. So I'll give you a moment to do this one. One more minute. Okay, so I'm going to explain this one now. So the system is in static equilibrium, which means that the forces acting on the car must balance out. So the F out force equals to mg. Similarly, F in is the weight of the person. So mpg, m of person. So we know that the pressure going in must equal to the pressure going out, which means that F in over A in equals F out over A out. If we rearrange a little bit, we want to find the mass of the car, which is in F out. So we want to find F out. F out equals F in times A out over A in. mcg equals mpg times A out is going to be 3, AN is 0.2. So if we simplify a little bit, we're going to have MC equals 900 kilograms. So this just goes to show how we can use Pascal's principle to lift very heavy objects with a smaller force. All right. So now we've got Archimedes' principle. Archimedes' principle, we're going to use this principle a lot more than Pascal's principle. There are a lot of problems on the F equals ma that involve Archimedes' principle. So Archimedes' principle basically talks about how objects float. How objects float. So why do objects float? This is because for any object inside a fluid, there's a force called the buoyancy force. I didn't spell that right at all. Excuse my bad spelling. Buoyancy. So this is the force exerted on any object that is inside a fluid. And the buoyancy force is always directed upwards. If I have a box in here, there's always going to be FB, a buoyancy force pushing the box up. Okay, so that's the nature of any object inside a fluid. There's always going to be a buoyancy force pushing this object up. So the net forces on this object are the buoyancy force and gravity, FB and FG, okay? So if the force of gravity is greater than the buoyancy force, the object will sink. If the buoyancy force is greater than the force of gravity, then the object will accelerate upwards to the surface. If they're exactly equal, then the object will float in equilibrium. So how do we find this buoyancy force? The reason the buoyancy force actually exists is because of the formula P equals rho GH. The fact that pressure increases with depth, which means that the pressure exerted on the box from the bottom, P2, is a lot bigger than the pressure exerted from the top, because pressure increases with depth, which means that there's a net pressure going upwards, a net force going up. So this is what causes a buoyancy force. Buoyancy force is caused by the differences in pressure on the top and the bottom of the box. So how to calculate the buoyancy force is going to be equal to P2 minus P1 multiplied by A, right? So this will be the buoyancy force. But this formula is not perfect yet, so let me change it a little bit. Let's say the distance between the top and the surface is going to be h1. The distance to the bottom is h2. Okay? So P2 is going to be rho GH2, and P1 is going to be rho GH1. Buoyancy force is equal to that. Factoring a little bit, we get rho GA times h2 minus h1 equals buoyancy force. Okay? And note how h2 minus h1, what is that? That's equal to the height of the box. Okay, so let's replace that with h, which is the height of the box. So now we can see how a times h, volume equals a times h. So let's replace this again. FB equals rho. This is the rho of the water. G times volume. And this is the volume of the box. We know that mass equals, mass over V equals rho, which means that rho V equals mass. Oh, look, rho V is in here. So FB equals mass of water times G. So this basically means that the buoyancy force is equal to the weight of the water that the box displaces. So the buoyancy force is equal to the weight of the water that I can fill this box up with. Okay, so are there any questions about the buoyancy force? So the buoyancy force is equal to the weight of the water the box displaces. And this is basically what Archimedes' principle is. The buoyancy force acting on any object in a fluid is equal to the weight of the water that it displaces. All right. So this means that if we look at this formula again, let me change it back into rho WG times V. The volume of the box. So the net force acting on this, F net, is going to be the buoyancy force minus the gravitational force, M of the box, times G. The mass of the box is equal to rho times V. So it's going to be equal to the rho of the box times the V of the box times G. If we factor out some stuff, we have V of box times G, rho water minus rho B, F net. So this shows that if the density of the water is greater than the density of the box, the object will accelerate upwards. If the density of the box is greater than the density of the water, the box will go downwards. Okay, so this is why steel will sink in water and wood will not sink. Okay, so this is basically Archimedes' principle. Are there any questions about this? Okay, so one last example I would like to go through is in the case where if we have a log floating partially above the water, right? When we see a log floating in water, some of it's above, some of it is not. And this is because since the log is in equilibrium, the buoyancy force is balancing the gravitational force. Right? Since the box is not moving, the buoyancy force must equal to the gravitational force. And as you can see here, the water displaced by the log is now less, which allows the buoyancy force to go down and to equal the gravitational force. So this is why only some of the log will be in the water to supply that buoyancy force. Okay, so that's one example of how Archimedes' principle applies to an object floating on the surface. All right, so let's do some problems. Here are two problems. I'll give you guys 5 minutes to do these. And when you get your answer, please chat that to me. One more minute. Okay, I'll explain now. So for the first one, how much force is needed to lift the statue from the bottom of the sea? Let's draw a little diagram here. We first have the force that we're going to pull the statue up with. We've got the gravitational force, mg, and we've got the buoyant force that helps us lift the statue out of the sea. So the actual force needed is less than the weight of the statue. Okay, so we know that F will equal to mg minus FB. So you already know what mg is. So let's find the buoyant force. The buoyant force is equal to the mass of the water displaced times g, which means that it's the density of the water multiplied by the volume of the statue times g. So now it's going to be 1,000 multiplied by the volume of the statue. So we got to convert this into meters cubed. All right, 3 times 10 to the 4th. We divide that by 1 million, which is 10 to the 6th. So it's going to be 3 times 10 to the negative 2, 0.03 times g. So the buoyancy force is going to be equal to, I think it is 30, around 30. Okay, 30 newtons. Let me check that real quick. Oh, actually, it's around, it's like 294 newtons. All right, this is the buoyancy force. So the net force we need to pull the statue up is going to be equal to 70 times 9.8 minus 294. So this is going to be equal to 362. All right. So for the next one, basically the same thing. The reason that the scale only reads 13.4 kilograms is that the net force acting on, there's the buoyancy force acting on the crown, which makes it apparently lighter. Okay. So one way you can establish this is that the ratio of the net force to the weight is equal to 13.4 over 14.7. Of course, you could have analyzed it like with the previous problem, but I'm going to take a little shortcut here. Okay, so if F net over F weight is 13.4 over 14.7, this means that FB over F weight is going to be equal to 14.7 minus 13.4 over 14.7. So what's 14.7 minus 13.4? I think that is 1.3. So the buoyancy force over the weight force is 1.3 over 14.7. That's the ratio. So we also know that buoyancy force is equal to rho of the water times V crown times G. The weight is going to equal the density of the crown times the velocity of the crown times G. Oh, look, we have things that cancel out. The rho of the water over the rho of the C of the crown is going to be 1.3 over 14.7. Rho C is going to equal to 11.3 times rho water, which is around 11300. So let's check our table to see what object has this density. And I think it happens to be, well, I think it is silver. All right. So the crown is made of silver. It's most close. Maybe it's lead. Okay. So I think it's actually lead because the density of lead is in fact 11300 kilograms per meter cubed. Okay. So you could have analyze the forces, just like with this problem, but I took a little shortcut here, because there are always multiple ways to do these problems. All right, we've got 2 more problems. These are the last problems for today. I'll give you 5 minutes again, and when you get your answer, you can chat that to me. One more minute. All right, I'll explain this one now. So for the first one, let's just draw out a diagram. We have the log in the water, and some fraction of the water is submerged, and some of it is not. So we know that the buoyancy force in this case, since the log isn't moving, Fb must equal to mg. So Fb equals mg. This means that the mass of the water equals the mass of the log, right? And this is the mass of the water displaced, which is the water that can fill up this area, okay? So now we're going to use rho equals m over v, m equals rho v. So we're going to replace m over here with rho water times v submerged times g equals ml, while the mass of the log is going to be equal to rho log times the total volume times g. We can cancel a little bit. The fraction submerged is going to be v sub over v total. So it's going to be v sub v total equals rho log over rho water. 300 over 1,000, 3/10. All right. So now for the next one. A large balloon is filled with helium. What volume of helium is needed to lift up a load of 180 kilograms, including the empty balloon? So let me draw the balloon here. My artistic abilities are very good. So we know that the buoyant force is going to balance out. Well, first of all, it's going to have to balance out the weight of all the cargo and the balloon, 180 times g. But also we need to consider the weight of the helium, because the helium is also being pulled down by gravity. Mass of helium times g. So we know that the force, buoyant force, is equal to mhg plus 180 times g. Okay, so what's the buoyant force? Well, buoyant force, we know that FB is going to equal to the mass of, well, in this case, it's going to be air, actually, not water. Mass of the air displaced times g. We're going to use rho equals m over v, rho v equals m, once again. So m air is going to turn into rho air, volume balloon, g. Okay, so rho air equals, well, mass of the helium, that's going to equal to, we can replace it with rho v again. So mass of helium is going to equal to rho helium times v. Okay, so now all we need to do is isolate v in this equation. So let me move this to the side. I think we're going to have VB equals 180 over rho air minus rho helium. The rho of air is, from our table, it is 1.29. From our table, the rho of helium is 0.179. So calculating it, give me a sec. Minus 0.179. 180 divided by that. 162 meters cubed. All right. So that is the answer. Are there any questions? Okay. Let me move this out of the way. That's going to be the end of class today. Hope you guys enjoyed. See you guys next time. And next time, we're going to be talking about fluids in motion. What happens when a fluid is moving, like when water drips from your faucet. Okay, so see you then. Bye.
Bye.
Bye.